Okay, we are now talking about fiber optic cabling. This is part 3 of chapter 4. Okay, so with fiber optic cabling, of course, we've talked a little bit about this, but bits are transmitted as pulses of light rather than electricity. So a light on for an amount of time or a refresh would be counted as a 1. A light off for an amount of time or a refresh, a cycle, would be counted as a 0. So fiber optic cabling is actually pretty magical, and as far as I'm concerned, I can understand. I mean, baseband and broadband is a little bit magical too. I understand baseband a lot better than I understand broadband, but again, the cycles are measured at incredibly high speeds. We're talking microseconds and nanoseconds, very, very small amounts of time. But fiber optic cabling is immune to EMI, so that's a big plus in the fiber optic cabling camp. It's highly secure. It's completely immune to electronic eavesdropping. So in order to eavesdrop on a fiber optic line, you actually have to cut it, splice into it, terminate it into a device that's going to pull data off of that line. So it would take a little bit more work, and if you cut a line, that's going to raise some red flags with people, and they're going to be able to go find you and quickly shut you down. So, but with twisted pair cabling, you don't even have to cut the line. It could never go down. You just clamp on an electronic eavesdropping tool. So, that being said, fiber optic, again, it's highly secure in comparison. Composition of fiber optic cabling varies slightly, but for the most part, it is a glass fiber called the core, surrounded by a concentric layer, meaning even layer of glass called the cladding. So the core is where the actual transmission is happening. The cladding is just to keep the light within that so that it doesn't bounce around too much. But then the fiber is jacketed in a thin, transparent plastic material called the buffer. Okay, so the core is very, very pure, clear glass, and then the cladding is less so. But this is the typical composition of fiber optic cabling. It varies slightly from type to type, but we're going to look at sort of the two types of fiber optic cabling in a minute. Okay, so the buffer is the plastic sheeting around the outside. All right, so let's look at this. Keep going here. So here's a quick glance at that. This is a fiber optic cable that includes several strands, but you only need a single strand for one way of communication, but you need two to go both directions when you're talking about baseband communications, which all that we talk about today is all baseband. There is some broadband stuff that requires only a single fiber optic strand. We're not talking about that today. We're talking about baseband only, meaning it does send signal as a digital signal, not an analog signal. Okay, so there's no frequency variation. It's all just one color of light, in other words. So if you look closely, you can see real small here at the end. There's your fiber optic strands. Then you've got your inner sheathing, a layer of Kevlar for strength so that you can't snap it, and then an outer sheathing. So fiber optic strands, particularly in baseband communication, only carries data in one direction. So you need two or more strands for network communication, for a network connection. And that's where, unless you're talking about a ring, so in the case of a ring, it can go in one direction and ultimately make it to its endpoint. That's where FDDI was a little bit more practical. But even with FDDI, they did a dual ring for redundancy. So even still, you still needed two strands. But if you're using fiber optic cabling for backbones, you often run it in bundles of 12 fibers or more. And the whole point of this is that even if two are used, it's a good idea to have more in case you expand for some reason, or if something breaks, you can quickly re-terminate. If something breaks in an attic in a place that it's really hard to re-terminate and splice, it's a difficult thing. And actually, fiber optic cabling, this isn't fiber optic, but you can kind of imagine this was, if you bend it, oops, I can't see myself, so, oh well, I guess I can't see, but if you bend it around like that, it'll actually snap the glass inside the wire. So I'll show you guys a piece of fiber optic cabling tonight in class, but until then, you can just use your imagination. So Some tests have shown that glass fibers can carry up to terabits per second, 1,000 gigabits, but this has never been actually implemented. To my knowledge, no technology exists that can actually transmit or encode at that speed. So there's no network interface cards that are capable of writing at that speed or reading at that speed. These are just preliminary tests that eventually one day we might get to that point, but you'd have to remove the limiting factor of your computer using copper cabling to transmit internally. So once we go to full fiber optic computers, which that technology has been discussed, and there's actually some experimentation going on in different universities, but there's nothing implemented in mainstream networking. So some fiber optic characteristics, the sort of maximum length, minimum to maximum is 2 kilometers is sort of the low end fiber, and then up to 100 kilometers with high end fiber. So it's about half. So 2 kilometers would be about a mile, a little under, or a little over rather, and then 100 kilometers would be a little over 50 miles. So 62.14 to be specific, I guess, according to the slide. Bandwidth currently available, 10, 40, 100 gigabits per second, depending on the type of fiber optic cabling you're using. 100 gigabits per second is about the fastest that we've ever gotten fiber to go. So the bend radius, 30 degrees per foot. Essentially, you have to think if you have a foot of cabling, then I don't know how to demo this without a cable. The bend radius, if this is about a foot, which I would say it's about a foot, then you would be able to bend it about 30 degrees. So you have to guesstimate, but sort of use your imagination here. But I don't have a protractor, so I'm not going to say this is exactly 30 degrees, but it would be about like that. That's your bend radius. So in order to complete your circle, it would be about a foot circle. A foot in diameter, I should say. So that's an approximation, but again, the bend radius is a lot larger with fiber optic cabling because it's glass. Glass can't go around those curves, or light can't move around the curves as fast if it's a lot tighter. Now you can wrap it a lot tighter in terms of the actual wiring, the actual strands itself. Like they're not going to snap necessarily, but it's not recommended for the speed of the connection. It's very difficult to install and maintain. If anything breaks, you got a real problem on your hands. It's highly expensive. It's the most expensive type of cabling available, and it ranges in price from about $1 a foot. Well, I don't know if that's the lowest price. You could probably go a little cheaper, maybe 75 cents a foot, up to $7, $8 a foot, depending on the type of cabling you get. Especially if there's multiple strands, it can get really pricey. The connector types, there's several, but it's not like a patch cable where there's only one type that's really used, RJ45. There's several types of connectors that are used for fiber optic, and we'll look at some of those. Security, very, very secure, not susceptible at all to eavesdropping. No interference would affect fiber optic cabling. So the type of connectors: ST, SC, LC, MTRJ, FC, MIC, SMA. The most common types, I would say. It's between ST and SC. LC is pretty common, and FC is pretty common, but SC and ST are the most common. So we'll look at what those look like. Here they are. So SC and ST. SC is becoming more common now. But you had a lot of ST for a while. This is what was used by FDDI. So when you see FDDI, it's 2 of these connectors, and then you plug that into your FDDI switch, essentially. Okay, it's really an FDDI MAU if you want to think about it like that, or a media converter would be a better way of thinking about it. Okay, so fiber optic installation. It's a lot more difficult to install. The cost is much higher for all of the materials to terminate, and the education to terminate it is much more expensive as well. You most likely would need to take a class. I have a video of somebody actually terminating a fiber optic cable. It's pretty intense. You have to line it up with like a microscope and then get a perfect mesh, and then it fuses it with an electronic signal, or with an electronic current. It's basically welds the two together by melting them with electricity. It's pretty intense, very cool, but very expensive and very time consuming, requires significant training. So two types of fiber optic cabling: single mode fiber and multi-mode fiber. The most common type that's used in LAN application is multi-mode fiber because it's a lot cheaper. It's about the width of 2 human hairs. A human hair is about 20 microns thick, 25 microns thick approximately. And multi-mode fiber varies in length, width across a span. Let me do a little drawing here. And again, I can't really see this, so I'm hoping that you can. I'll try and do my best. I forgot to put my webcam capture on the screen so I could see it, but so if you were to look at an up-close shot of multi-mode fiber, it would look like this, and this is 50 to 62.5 microns. Okay, now we're going to look at some single mode fiber. I should have drawn this a little bit skinnier here. In fact, I will. So, and this is a consistent 8 microns thick. So, multi-mode fiber, it uses an LED light to emit the lights that's actually being translated as a signal, so it uses LEDs for encoding. So the distance isn't as long, so if you want to think about how the signal translates, if this is your little light bulb here, let's just draw up a little LED light right here, okay? If this is transmitting signals, they're sort of going off in whatever direction they want and ultimately bouncing their way down the line. Okay, and there's many waves of light that are all going, right? And ultimately, they all make it to their destination around the same time. Okay, when you're talking about the speed of light, it's sort of irrelevant, but you can't go over very long distances in this way because eventually attenuation sets in, other factors kick in that would prevent you from going very long distances. But then with single mode fiber, SMF, you have a laser light, which a laser, if you're not aware, is a focused beam. Essentially sends light down the line in a perfect straight line, like straight as an arrow. I mean, besides the fact that light travels like a wave and a particle, so it's kind of funky how light works, but that's sort of the properties of light that they utilize. So a laser focuses it in a direct line, and so it's able to go. That's where you get your 100 gigabit per second, and that's where you get your 100 kilometer distance, where with multi-mode fiber you don't get nearly as high of speeds or distance. Okay, so some cable testing equipment. So we've looked at fiber, we've looked at copper. Now you might need to, you've built your cabling, now you need to test it. So there's a couple of different types of testers. A cable certifier would be for testing the standardization, making sure it meets the criteria of that type of cabling. Essentially, you would set it to Cat5e and make sure that it's meeting standards for Cat5e. Set it to Cat6, it checks the standards for Cat6. If you're using fiber optic, it would check your speed and make sure you're meeting criteria for fiber optic. So cable certifier is a little bit more high end. Then you have a basic cable tester. This just says, yep, sure works, good to go. So, and I always talk about how usually these things make some kind of beep sound if you're good, sad sound if you're bad, happy sound if you're good, sad sound if you're bad. We'll actually use basic cable testers tonight. And then you have what's known as a tone generator. A tone generator is sort of there's an industry term for this called a fox and hound. Essentially, you plug one end into your wall jack, and then it allows you, I wish I had one to sample for you guys, but it makes a noise. It goes and follows the cable through the walls. So it puts a signal on the line, a tone, that you're able to follow through the walls. It's a tone generator and sniffer, if you want to think about it like that. A lot of people call it fox and hound. That's sort of a common term, but it's basically just a little thing that sends a signal onto the cable that actually translates to audible sound as you follow it through the wall. Okay, and it bleeds out from the wire so that you don't have to be touching it. You can trace it through a wall without being able to see it. Then you have a TDR. This is for the purposes of measuring the length of a cable. It's also very valuable for finding a break if it's a fiber optic cable. So you use an FTDR for fiber optic, I believe. Anyways, this is a time domain reflectometer. Basically, it sends out a signal that gets bounced back. So if there's a broken wire, or if it just hits the end where it's terminated, you would know the length of your cable. So it measures cable length based on how long it takes for the signal to come back. So and then you have a multimeter. A multimeter, of course, we've looked at. You can test continuity, resistance, and everything else. But I wouldn't say this is a super handy tool for wiring a network. It's more of an electrician's tool. But there might be some application. I've never used a multimeter one time in any networking related environment. Then you have an optical power meter. This is for testing how clean a fiber optic cable is. So if you haven't cleaned your ends properly, you might not get a very good signal. So you would use an optical power meter to verify that the signal is making it through and that you don't need to clean your ends. Okay, you guys can go through and look at those. So now we're going to talk about wireless networking. I'm going to stop the video and finish this off. I believe we only have just a few more slides, so finish this off in the final video.